Hello everyone, I'm one of the authors of this paper, Shen Tong, from Beijing University of Technology. Today I'm going to talk to you about our work, conversation and recommendation. Knowledge-enhanced personalized dialogue system, as this title describes. Our work is a conversational recommendation system with restaurant recommendations as the application scenario. And then I will introduce our work. The first part is our motivation. After learning the existing work, we have the following ideas. First, we consider a situation in which the system action can be divided into interaction or recommendation at each turn in the conversation. Then the model can use more targeted method to generate response. Subsequently, we consider modeling user preference over the knowledge base. Moreover, the ambiguities in user requests are difficult to handle. For example, a user requests for directions to the restaurant. This word direction can be interpreted into parking or public transport direction information in the knowledge base. And we think current recommendation method is usually limited to the performance due to the irrelevant information in conversation. So in response to these points, we have made the following contributions. First, we use a fully connected layer to learn the dialog state and predict the probability of the next action. And we proposed a method to calculate user preference scores to recommendation ranking based on the knowledge base. And we design an information inference method to handle ambiguities in user requests by modeling user preference over the knowledge base. And we also apply multi-head attention to alleviate the irrelevant information in user utterance and dialog history. Here is an example of the conversational recommendation. We can see that in this figure, when a user requests a restaurant reservation, the system can get the user profile at the beginning and get to know the user instance during the conversation. After interacting with the user and according to the user's dietary and favorite food, an Italian restaurant may be recommended by the model. So we think the conversational recommendation usually include interaction terms and recommendation terms. In the next part, I will introduce the model. First, let's get to know the framework of the memory network. From this figure, we can see that the left part is a single-layer version of the model. In practice, we will use several hops to update the query iteratively. The profile attributes and dialog history are modeled in two separate memories, and the outputs of both memories are summed to get the final query. Before we introduce the follow-up parts, let's learn about the knowledge base. As the table shows, each row denotes an item, and each column denotes one of their corresponding attributes. However, a knowledge base is typically only available in a closed domain. So it is difficult to learn a low-dimensional representation vector for each item and relation by representation learning. So we convert each item and its attributes in a key value pair to help return the structured information. As for the overall architecture of our model, it is built on the basis of split memory network, and the three models we proposed are utterance encoder, user preference score, and information inference method. As for the utterance encoder, we apply the transformer encoder to model the dependence of the words in a sequence. Next, I will start to introduce our method. For the recommendation terms, we design a user preference score method using the correlation between the user profile and the restaurant attributes to reflect the user's preference for the corresponding restaurant. We compute the match between the user profile and each attribute of an item by taking their inner products, followed by a relo activation as the user preference score. Next, we use the scores to calculate the probability of the items via a softmax layer. Then the user preference over the items can be aggregated by the probabilities. Finally, we can get a vector with the same dimension as the result of the memory network. Note that the candidates that mention at least one item are used as recommendation candidates, and the others are used as interaction candidates. Therefore, all the candidates can be divided into interaction set and recommendation set. And then we harness the dialog state to generate the probability of subsequent action by applying a fully connected layer to learn the query and the dialog history, followed by a softmax layer, so we can get theta I and theta R. These two values can control the contribution of the user preference score and the user query. In this way, the model can pay attention to specific utterance and captures better user preference at the same time. And then next is our information inference method. At first, the user preference is applied to model the user profile is applied to model the user preference on all the different attributes. And we further consider the mutual influence among the restaurant attributes. As the selected item is the user choice during the conversation, we model the influence by learning the dialog history. In order to select the attributes that best meet the user need, we estimate the relevant attributes for current query, and then the weighted sum is combined with the result of the memory network. In the next part, we evaluate our proposed framework on the personalized BABI dialog dataset. In terms of task definition, displaying options means that the bot must use a reasonable method based on the user preference to sort the restaurant in the results. And the providing information means that the bot must learn to retrieve the correct knowledge-based facts tolerated for the user. And full dialog conducts a complete dialog to verify the above tasks. From the table, we can see that our KB-enhanced memory network perform best on all the tasks among the memory network-based models. Since we consider the case where the interaction turns and the recommendation turns in conversation, the user preference scores method based on the knowledge base can help our mod perform best on displaying options. As argued in the paper of split memory network, memory networks cannot effectively use knowledge-based facts in the dialog. Personalized memory network and our model predicts the user preference according to the knowledge base and achieve superior performance on providing information. Since we further consider the attributes of the restaurant mentioned in the dialog and balance the relative importance of multiple attributes, our performance is even better. For dialog test all of the previous tasks, since our model has significantly improved on displaying options and providing information, it also leads to better performance on full dialog. And then to evaluates the contribution of the multi-head attention. We obtain the probability over the memory with and without multi-head attention in the memory network, respectively. As shown in the figure, the darker the color of the corresponding grid, and higher attention is paid to the memory. We can find that the attention distribution with multi-head attention is more concentrated. The difference in the probability over the memory also affected the final product result, that the model with multi-head attention shows better results in the prediction. To validate our thoughts, we perform extensive ablation studies on user performance score method. This table reports the accuracy on displaying options and the contribution of the recommendation terms to the overall accuracy. In detail, method 1, which does not divide the candidates, and the method 2 means which only apply user preference scores and divides the candidates. And the method 3 means that which removes the theta I and theta R, so that we can attribute the superiority of the UPSM to its two properties. One is the UPSM learns dialog state to consider a strategy decision, which can determine an appropriate timing to push recommendations. Secondly, UPSM leverages the knowledge base to apply user performance scores, which better match the user preference and the attributes of the restaurant. Next is the analysis of information inference method. As we mentioned, the probability of choosing parking or public transports may be affected by the price range of the recommended restaurant. The statistic of the prediction on this instance is depicted in the figure. And we can find that the bot prefers to provide parking information if the restaurant in the moderate or expensive price range. Meanwhile, the bot tends to return the public transport information if the restaurant is cheap. So the above results confirm our model does learn the mutual influence among the attributes based on the knowledge base. Finally is the conclusion. First, our strategy decision approach indeed improves the recommendation accuracy by capturing user preference through the knowledge base. Next, the results suggest or hypothesize that the existence of the inherent relationship among the attributes, and our model does learn the mutual influence among the attributes based on the knowledge base. That's all. Thank you.